Okay, welcome back, ladies and gentlemen, to Physics 8B live streaming this fall 2025. And boy, oh boy, what a semester to be taking Physics 8B. You are one of the lucky few that either has Bordell or Speleo. And what that means is that in one way or another, your life is Physics 8B this semester, pretty much. And Physics 8B is your life. I'm not trying to discourage anyone. It is what it is. It's both instructors have, their pros and cons, and I'm not really there to take a side or to stand against anyone, but they both are pretty demanding when it comes to exams, and that's what I think we need to take away and focus on. It is not impossible to do well in Physics 8B. It is not impossible to do well in Physics 8B if you take it with Bordell or Speleo, but it does help to know what you're up against and know that you have to be prepared. So this is not a course where you wait till end of September to start studying for midterm one. That's not how it's going to work. If you thought there was a lot of material in 8A, there is more material in 8B. And the bad news is, well, the good news first is that you've taken 8A, so you kind of know how to play this game. The bad news is 8B is far more conceptual and abstract than 8A. A lot of 8A can be visualized. A cylinder rolling without slipping down an incline, check, I can visualize that. Magnetic charge moving through, an electric charge moving through a magnetic field or being accelerated across an electric field, harder for me to visualize. You've never seen an electric field or a magnetic field, you never will, and that's the first hurdle of 8B, is to not try to visualize everything, because for the most part you can't. So instead we have to focus on the rules that we use to draw and quantify these things that we cannot see. Electric fields being the first in line. And so there are rules to draw electric fields. There are rules to quantify the magnitude of an electric field at a given point, and to then get the electric force that it might exert on some particle. But we just have to learn these rules and get as comfortable as we can, as quickly as we can. And that's pretty much it. Again, visualizing is almost impossible. So that's just a quick heads up. It's been a minute since I've live streamed Physics 8B. The whole summer was quite busy, and the studio is not quite back up and running yet. I changed it, and so I'm not keyed in, and there's a few things missing, but we'll get there by probably by midterm one if all goes well. However, some things have not changed. So if you want to have access to this live stream, you can go to slackademia.com and you can enroll in a course called 8B Livestream. And it is a free course. You don't have to pay anything. It has all these videos. I'm going to do one live stream a week where we're going to go over the topics of the week and some practice problems. And it'll have all the live streams in that free course. It will also have the homework problems. So, some of you already know this and are already doing it. Send me the PDF of the homework set, and I will post the homework problems and their solution in that free course so that you can get solutions to the problems, because Expert TA won't give you solutions after you've solved it. So at least you'll get something out of homework, hopefully. If you want to get in touch, you can go to facebook.com/myslackademia, probably the easiest way if you want to DM me directly. You can also email me through the website if you want. There's a little form for that, but faster to go through Facebook. And this is a bit of a new format. I mean, it lives in the same place as before. It's a bit of a new format because one of the main complaints last semester in the spring was that doing 2 live streams a week just didn't really make sense, because the first one was really lecture heavy. I mean, the goal was to pretty much summarize lecture, but it ended up lasting a long time, and I always basically ended up just covering the whole lecture, which a lot of you have said, well, is not as helpful as practice problems. So what I'm doing this time around is I'm going to do a quick summary of the important topics, but the focus is going to mainly be on problem solving. So that we know what types of problems to expect, and it's also we talk about problems that kind of fit between lecture and discussion. Another big complaint that I usually get was that well, there's two main complaints. There's one is that you look at a problem and you don't know where to start, even though you've gone to lecture and you know your formulas and you've taken notes. The other one is that sometimes in discussion, the problems that are given seem to be too complicated off the bat, or sometimes they're just completely off topic and just not very helpful, a bit more conceptual than quantitative. But most of the time what I hear is that the problems are just too hard off the bat, and there's no building up your skill set to be able to at least attempt the problems. You may not know how to solve it fully, but at least get started. So that's what this is trying to address. We're trying to go from, okay, you've gone to lecture and you have some sort of knowledge about electric fields. Let's summarize really quickly the important topics, and then let's do some problems where we take a little bit of time and we talk through the big confusions and kind of get you some skills so that when you do go to discussion, you at least can attempt the problems that you're being given. And then the goal, of course, is that after live stream plus discussion, you should be able to do problems on your own. And as you know from 8A, I would highly recommend that you find problems to do on your own. You can find them in the study guides or the master classes on slackademia.com. That's true. If you want to find them somewhere else, I actually don't care. But do problems, and do problems that have solutions, because that is going to be the fastest way to figure out whether you know or not the material and you're able to perform at an exam level. Okay, so let's start with electric fields. Electric fields is the first chapter in 8B. It always is, it has to be. And 8B is very linear compared to 8A. 8A has some variation. Some people throw gravitation in somewhere. Some do energy before momentum. Some do it the other way around. And there's some leeway as to how you organize some chapters in 8A. That's fine. In 8B, there really isn't. You have to start with electric fields, and then it's very linear from then on out. So we are going to be starting with electric fields. We're going to do basically two things today. We are going to talk about point charges and remind ourselves what the electric field created by a point charge is and what an electric field represents. And then we will see how an electric field can exert a force on a charge. And then we'll do problems. But those are the two main things. So we're not trying to cover too much ground. We're just trying to talk about point charges, because that's usually where we start. And then electric fields in general. In particular, it'll get us to Coulomb's law eventually. But we're just trying to hit on those topics first, do some problems, and then next week we're going to do Gauss's law. That'll be a different beast altogether. But Gauss's law is how do I derive an electric field versus it's not really, presumably you already know what an electric field is, in other words. It's just a method to derive it when there's enough symmetry. So let's talk about electric fields, shall we? And let's start with point charges, right? So point charge and electric field, call it capital E. And it's a vector, so we'll put a little arrow above the electric field. Okay, so a point charge is a mathematical point. It has no size, has no top, no bottom, no front, no back. It's just a mathematical point. Okay, we draw it something like this. And it could be positive or negative, because charge could be positive or negative. Okay, and what it does, and it'll make a little bit more sense perhaps once we tie it to Coulomb's law, but I want to start with electric fields, and there's a good reason for that. It's like, if we start with Coulomb's law, you tend to think Coulomb's law applies to everything and you want to use it all the time. Coulomb's law is a consequence of the electric field being of a certain form for a point charge. So I'm going to go the other way. I'm going to start with electric field, and we're going to build our way to electric force. Now, electric field created by a point charge plus Q is going to radiate out in every direction of space. Okay, so this is actually three-dimensional, right? So, and now you could draw as many as you want of these field lines, right? Because the electric field's everywhere. So I'll draw a few just to make my point. Perhaps I'll draw These guys here, these are the main ones, right? And actually I'll just draw 4 of them for this guy, but of course it goes in all directions, right? Everywhere you look there's an electric field that radiates out, including out of the page and into the page, right? So think disco ball, right? The light that bounces off a disco ball radiates in all directions, and that's the same idea for this thing. Okay, so typically we would write E like this next to one of these, and these red things are called electric field lines. And electric field lines are there to represent the electric field everywhere in the space surrounding the charge. And here they're just radiating out, so it's pretty straightforward to represent them. Now, that's a positive point charge. Okay. Now a negative point charge, call it minus Q. In fact, let me do this. Let's even call it minus 2Q. Okay, we'll double the amount of charge in magnitude, is going to have electric field lines that are also radial, but they're radially inward, right? So they come in from all directions aimed at the point charge, right? So they go in exactly the opposite direction, really, of the electric field lines for the positive point charge, okay? Now, one of the rules that we have about field lines that most of the time we don't even bother to apply is that we tend to draw a number of field lines that is proportional to the charge. So if Q leads to 4 field lines, if that amount of charge means 4 field lines, then minus 2Q, which is double in magnitude, means I need twice as many field lines. So I'm going to get my field lines that are coming in like this. That's only 4 of them. I would need 8 to represent the fact that the charge here in magnitude is twice as large as the charge on the left, okay? But of course, this only makes sense if you're trying to represent the field lines of this negative charge minus 2Q relative to the field lines of this charge Q. So most of the time we don't bother with this rule or this convention, but it's good to know because occasionally you will have to draw a number of field lines that is proportional to the charge that creates them. Okay, so the electric field, again, radiates in or out, depends on the charge being negative or positive, and it exists because charge exists. In other words, it is a property of the space surrounding charge. So let's write that down just to get a few definitions in. So E is a property of the space surrounding charge. So if you have charge in the space that surrounds it, you have an electric field, okay? Now, what it represents is the amount of electric force per charge at a point. So it, and this is very important, so it represents, it's a weird quantity, right? It represents an amount, or rather the amount, I should say, the amount of electric force per unit charge at that point. Okay, or at that point, at a point, I haven't specified which point. So let's say it represents the amount of electric force per unit charge at a point. Now this is really important because electric fields are quite abstract to us. We don't fully, it's very hard to relate to them and to understand what we're talking about. And what it means is that at any point in the space surrounding charge, if you were to put another charge, you would get an electric force between the two, right? That new charge that you put in here, if you put a test charge, is what we call them usually, so, which is a charge that we use to perform a test. Well, then if Q test is positive, it's going to get repelled by a certain amount of force. And the argument is that, well, that amount of force per charge was there from the beginning, it's the electric field, and now all of a sudden if you put Q test at that point, you're going to get a certain amount of force depending on how big Q test is, right? So in other words, any charge We'll call it Q test just to keep the same notation. Placed at a point where the electric field is E, experiences the electric force, or, well, experiences, yes, the electric force we'll call it F sub E is equal to, now E is force per unit charge, and it's a vector, so it has magnitude and direction. And so if E is force per unit charge, then multiply charge by E should give you force. And so that's the idea. Now, an imperfect analogy is if you imagine a river flowing down, the flow of a river downstream, if you were to take glitter and drop it in the river would carry the glitter downstream. This is not a perfect analogy, but the idea is the river is there, it exists in and of itself. If you place something else, glitter, in the river, then it experiences a force that pulls it downstream. Okay, so it's imperfect, but you can kind of make the analogy that if there's an electric field in some region of space, just because there's charge there, if you are to put another charge in that electric field, just like you put glitter in the river, that charge would experience a force. And the amount of force that it experiences is a function both of the electric field that you have in magnitude and direction, but also the amount of charge that you place, because the electric field is electric force per unit charge. So we'll come back to that formula in a bit, but for now, the point that I'm trying to get across is this. Electric fields are this weird thing. They have a magnitude and a direction, but really they are there to tell us how much force per charge we have at a point in magnitude and direction, so that then we can put a charge there and know how much electric force it experiences. It'll be Q test times E. Okay, so that's kind of the quick version, the quick summary of electric fields. There's two things I want to do before we move on to electric force and talk about that, and then we'll do problems. The first thing is the following. The first thing is, and this is a misconception that, it happens so often that I'm going to say it and you're going to forget it and I'm going to have to say it again later, but that's fine. I've done this long enough that I'm used to that. So I'm just going to put this here so that we can look at it, right? But I want to make a crucial point here. And this crucial point is that if Q creates an electric field E, the electric field E cannot have an effect on Q. In other words, you cannot say, oh, this is electric force per unit charge. Oh, look, I have charge. This charge must experience a force because of that electric field. You can't do that, right? Now, if you place a different charge that did not create E into this electric field, then yes, that charge will experience an electric force. But E cannot act on the charge Q that created it. And this is really important, okay? If I place a different charge, Q test, that has nothing to do with Q, in the electric field E created by Q, then yeah, sure, the test charge will experience the electric force. But this electric field cannot have an effect on this charge, right? Plus, what effect would it have? Would it pull this way? Would it pull this way? Would it pull this way? You can't even argue what it would do. But it's a really important thing to note, and it's a common misconception that, it could have an effect again on Q. It doesn't. So that's really important. And then what we need to write is the magnitude of the electric field created by a point charge. Okay, so E of a point charge So in the space surrounding a point charge, there's an electric field. It either radiates out if the charge is positive or in if the charge is negative. We get that in all directions of space. It's three-dimensional. But how strong is it, right? And does it get weaker when I move away from the charge, or what happens? Okay, so we are going to write this, and this is going to be one of the two important formulas for today. E is going to be KQ over R squared, and then R hat. I'm going to talk about R hat in a minute. And this is E is equal to, now there's two versions of it, and the reason is K is 1 over 4 pi epsilon naught R hat. Okay, so I'm going to box this whole thing. You can use either one. You will find that more often than not, if your exam has numerical values, has numbers, you'll probably tend to use K because K is 9 10 to the 9. It's really easy it's an easy number to deal with. Whereas epsilon is a weird value, and it's not obvious how you would compute 1 over 4 pi epsilon naught without a calculator. Now, overwhelmingly, all exams have moved to variables only. That wasn't always true for 8B, but it's becoming more and more true these days. So unless there's been a major change in how either instructor teaches, I would anticipate a variables only exam. So, but that should be consistent with what you did in 8A too. Anyway, the point is K and 1 over 4 pi epsilon naught are the same. K is equal to 1 over 4 pi epsilon naught, but it's just, there's nothing special about K in the sense that K is not a physics constant, right? It's just, this is what this quantity shakes out to be. And so K doesn't represent anything physical. It is in Newton meters squared per Coulomb squared. Now epsilon naught does represent something. It measures how easily you can establish electric field lines in either vacuum or air. And for our purposes, vacuum and air are pretty much identical, even though in reality there's a slight difference, but we're going to ignore that slight difference. So epsilon naught is a physics constant that measures something, but K is just what you get when you compute 1 over 4 pi epsilon naught. This is called Coulomb's constant. But you can present your answer in terms of K or in terms of epsilon naught, up to you, unless the problem doesn't leave you a choice, in which case you have to do whatever the problem tells you to do. But those two expressions are equivalent. Now, while we're at it, and we'll come back to this, R hat is a vector that means, all it means is radially outward. That's what it means. And it's a very useful vector to have because we have x hat or I hat, same thing, which means to the right typically, y hat or j hat, which means up. So we have to the right and up, but we don't have, like, neither of those work for radially outward or radially inward. And r hat would be radially outward, minus r hat would be radially inward. And so it's a useful quantity to have, especially when you have electric fields that look like this, because they're radially outward or radially inward. So it's a new unit vector, but we're not going to spend too much time on it because most of the time we just end up ignoring it and reverting back to x hat, y hat anyway. But I will put it in the context of an example so that we kind of understand what's going on. Okay, so we have, we've covered electric field created by a point charge, or at least a summary of it. Let's talk about the electric force. Acting on a point charge. Okay, and then you're gonna really see how this all comes together, hopefully. Okay, what is the electric force acting on a point charge? Well, that's just a very simple formula. But before I write the formula, I want to draw things out a little bit. So here I'm going to draw an electric field. And I know it's likely created by some amount of charge. I don't know what that amount of charge is, where it is, what it looks like. I don't care. Like some machine, let's say, creates this electric field, and I'm happy with that. I don't need a better explanation. I'm just told there's an electric field, that's what it looks like. Cool, check, we're done. Now what I'm going to do is I'm going to take a charge Q, you could call it a test charge if you want, same thing, but little q, and I'm going to place Q in this electric field. And I'm going to argue that depending on the charge, being positive or negative, you get a force in one direction or another with a certain magnitude. And so here, first let's write down what we wrote before, which is that the electric force is going to be the charge Q multiplied by the electric field E, because E is electric force per charge. So if I multiply E by Q, it stands to reason that I get force. Okay. Now, quick math recap. This is a number, right? It's positive or negative, but it's a number. So I have two vectors that are proportional. Sometimes we'll call them collinear vectors in math. But the point is, I have a vector that is proportional to another through a number. If this number here is positive, both these guys have the same direction. If this number here is negative, these guys have opposite directions. And that's really crucial because charge could be positive or negative. So if I come in and I place a charge, I'll write plus Q, but the plus is optional, right? So if we don't write plus Q, it's presumably because Q is positive. If I write plus Q, placing Q in an electric field that was created by something else means Q experiences the electric force. That electric force will be in the same direction as the electric field because Q is positive. So this is going to be a force Fe is equal to QE in that direction. So it gets pulled in the direction of the electric field because it's a positive charge. However, not all charges are positive. Some of them are negative. So I'm going to place minus Q here. And I'm doing this separately from plus Q, right? Let's assume plus Q is removed so that these guys don't interact with each other, right? I'm just doing one charge at a time. If I place minus Q in this electric field, well, minus Q is a negative charge, so it experiences the electric force, but the electric force goes the other way because now I have Fe is minus Q times E. And therefore, the minus means that these two vectors, even though they're proportional, right, they point in opposite directions because the number, the constant of proportionality, minus Q, is negative. Okay. Now this is really important because one of the main differences off the bat between Physics 8a and Physics 8b is that in Physics 8a, you could argue 8a is the story of mass, and mass is always positive. So we're not used to contemplating two options. Mass was always positive, so that's it. The weight force always points straight down, never pointed straight up. It's not how it works. Okay, but charge can be positive or negative. And so that means it's either going to experience a force in the direction of E or in the direction opposite E. And that's really important to keep in mind because the behavior will be different for protons and for electrons, for example, or just in general for positive charge and negative charge. So, just something to keep in mind. Let me do the following. I'm going to add a page here because I don't want to jump into this problem right away. There we go. There's some other stuff I want to do first. Hey, I don't want that. There we go. Thank you. Jeesh. Okay, so that's the electric force acting on a point charge. Let's do an example. I'm do down here. I just want enough room. Okay, let's do an example to illustrate all this, and then we'll dive into a couple problems. Okay, so this, I'm just going to draw x and y axes. So this is going to be the y-axis, and this is going to be the x-axis. Okay. And I'm going to place a point charge here at the origin. I'm going to call it plus Q0. and it's fixed, right? So it's held in place somehow. Don't know how, but it is. Can't move, okay? And then I'm going to draw a few different points. So I'm going to draw point A here, point B here, and then point C here. And what I'm going to say is that XA is equal to 4 meters. I'm going to give you that. YB is going to be 3 meters. And then, you know what? Let's just draw this now. The distance here between the origin and point C, hopefully everybody agrees, is going to be 5 meters. I'm going to call that R. And this is going to be 5 meters. It's the Pythagorean theorem, right? Simply put, it's a 3, 4, 5 triangle. Okay, so I chose 3, 4, 5 on purpose just because it makes it easy. Okay, and just as a reminder, E, we wrote this above. E is KQ over R squared, R hat. So this is just a quick reminder so that we don't have to scroll up and down. Okay. Now we want to draw the electric field at points A, B, and C and give the magnitude and direction. Okay, so basically write the force in a vector form. And then, or sorry, not the force, the electric field in a vector form. And then we're going to look at the force. We'll use a test charge to figure out force, right? And so I'm just trying to illustrate something here and mostly trying to get us to wrap our heads around R hat, because R hat is this new thing and we're not sure what it is. But Q0 is a positive point charge, meaning that the electric field radiates outward from Q0 in all directions. Now there's a very important rule that, is this true that the electric field looks like this? It's like, yes it is, but am I going to draw all the field lines all the time? No, I have a life, I don't have time to do this, this is ridiculous. So as true as it may be, the rule is you do not draw field lines you do not care about. What that means is that if you're trying to draw the electric field at point A, you're only going to draw that field line. And typically what you'll do is you'll start it at point A. So at point A, the electric field from Q0 points out like this. Okay, this is going to be E sub A. Now you might say, well, how do you know? It's like, well, I know because guess what? The field line of interest would be this one, right, that radiates out and goes through point A. So if I'm standing here at point A with magic glasses on so that I can see electric field lines, that's what I would see. And again, I don't even draw the whole thing, right? I just draw a piece of it at A. But that's the only field line I care about, okay? Now, how big, or how strong, rather, is EA? Well, let's see, we can use this thing, right? And so EA is going to be, let me write it down here. EA is going to have a magnitude that's going to be K, Q0, divided by the distance between Q0 and A squared, which is XA squared. And EA as a vector, excuse me, has this magnitude, it's a positive number, and points to the right. So you could say, well, R hat, right? Because R hat in this particular scenario is this, right? Because R hat, here's the thing about R hat. R hat's a great vector because it just adapts to where you are. If you're at point A, R hat always means radially outward. Well, if you're at point A, radially outward is this direction. But then you might say, well, wait a minute, isn't that X hat? Can we not use X hat? It's like, no, that's cool. I'm okay with that. I'm okay with you saying that it's K Q0 over XA squared along X hat. All you're saying is that it points to the right. In fact, X hat is a bit clearer, right? Because X hat always points to the right. So then I'm like, oh, I get what you mean. Whereas R hat would mean radially outward. And then I might say, well, wait, radial outward from where? Oh, from point A, okay, then, if you draw it, then people understand. But the point is, I don't even have to draw X hat for people to know what I mean. Okay, so you're like, okay, well, I get it. It's kind of weird. R hat, why would we introduce R hat if it's going to be, X hat anyway? It's like, well, okay, hold on. Let's move on to point B, okay? Now, point B, I'm going to draw the electric field at point B. I only draw the field line that I care about. The field line that I care about radiates outward from Q0 through point B. And so it would be this field line here, except I only draw a piece of it because, I just need to roughly know what it looks like. That's good. And I draw it starting at point B. And then I can argue that, well, if I'm at point B, which direction is radially outward? Well, it's this direction, right? Radially outward from Q0 is going to be this direction. It's r hat, okay? Well, then E at point B is going to have a magnitude. The magnitude is going to be what? It's going to be K, Q0, divided by the distance between Q0 and B, which is YB squared, r hat. Right? And then I'll put an arrow above this to indicate that it's a vector. And I've given magnitude and direction. Cool. But then you might say, well, isn't it the case that r hat here is really just y hat? It's like, what's true? I agree. So I could do this. I could say it's K, Q0 over YB squared, y hat. That's valid. I can live with that. Now what about point C? Okay, well, point C, we'll do the same thing. I only draw the field lines that I care about. The field line that I care about would be the one that goes through point C. I don't have to draw the whole thing. That's kind of overkill. So I will draw the electric field radiating outward at point C. I will call it E sub C. And then now I'm kind of in a pickle. What direction? Well, r hat, and at point C, r hat goes this way. Okay. And so hopefully it makes sense. I'll write it here and then I'll bring it down so that we can put all electric fields together. But E at point C is going to have a magnitude that's K, Q0, divided by, well, the distance between Q0 and C, which is r squared, carried by r hat. Now the thing is, what is r hat? R hat is just r hat. I can't do any better. So that's the beauty and the curse of r hat, right? Because at point C, it's clear what r hat is. It's radially outward. It's this. Like, cool. But if you just read this, you're like, well, I'm not visualizing it. Without a drawing, I don't know what r hat is. Versus this, I don't need a drawing. I know what x hat's always to the right, y hat is always up, done, So the beauty of r hat is that you can use it anywhere. And wherever you are, it will be the radially outward direction. So in a sense, it adapts to where you are. But that's the problem at the same time, is that if you don't draw clearly where you are, r hat doesn't really mean too much. Okay. The other problem, and I'm not saying we don't need r hat. We definitely do, and we need to know what it stands for, right, and how to draw it. But the other problem that you have with r hat is that it's relative to Q0. And so if now you come and you add another charge, capital Q here, and you look at point C, well, now for capital Q, there's going to be another r hat. Now, I don't know, maybe I'll call it r hat 2 or something. I got to give it a different name. It's not the same r hat as this one. And that's the problem with r hat, is that it's relative to Q. So relative to Q0, this is r hat. Relative to another charge, if I add one, this is r hat. I'll just call it r2 hat. So the conclusion of this, and I'm trying to hopefully clarify things and not confuse things, the conclusion is the following. R hat is very useful in the sense that we had no unit vector that meant radially outward. And now we do. This is very useful because we have electric fields that are going to be radially outward along r hat or radially inward along minus r hat. But r hat will get the job done for both. The problem with r hat is that, well, yeah, it depends what point you're looking at. And then if there's more than one charge, you have more than one r hat, and like, fuck, like that just gets complicated. So what we usually do, even though r hat is very useful in ways, when we have a problem like this one, or like the one we're about to do later, we never bother with r hat. We're just going to break this back up into components. Okay, I'm going to say that this is an angle here, theta, all right? And that therefore the angle between the horizontal at point C and E sub C is theta. Let's see if I can get this to cooperate. I guess not. There we go. That's better. So this is theta. And okay, this goes back to physics 8a, yeah? But we need to be able to find components of vectors. So this is E, Cx. It is the adjacent component, so it's EC cosine of theta. And then this is the vertical component, ECy, which is relative to theta, it's the opposite side, so it's going to be EC sine theta. Okay, so what I would do is I would break it up into something like this, meaning that, oops, sorry, I didn't mean to do that, sorry, make a copy, meaning that, yes, I would probably write kq over r squared r hat at first, but then I would say, you know what, it really is kq 0 over r squared cosine theta along x hat plus kq 0 over r squared sine theta along y hat, right? I would break up into these components, right? This is EC right here. This is cosine theta, obviously. So this whole component is the x component. And so I have two components, an x component along x hat, a y component along y hat. And it's a lot easier to revert to that, even though when we give you the formula, apologies for so much scrolling, we'll give it to you like this, right? Because we don't want to go define what theta is and all that. We're like, no, just, like it's kq over r squared, r hat. That's a very condensed way of saying a lot of things. It says the magnitude. It also says the direction, radially outward or inward. So it's a nice compact notation. And as you know, that's the problem with physics. Is like F equals ma is also a nice compact notation. But in nobody's world is an exam problem as simple as just writing F equals ma. You have to write it along x and along y and combine them, and it's a whole ordeal. But it came from a very condensed formula. Okay, so that's kind of the name of the game. We'll give you condensed formulas because they package all the information nicely. But then you have to unpack it, right? You have to then do this and get E sub c in terms of components along x hat and y hat. Okay, so that is what I wanted to talk about, to touch on r hat. Okay, then I'm going to do this. I'm going to allow me to make a copy of this and just give me like 10 seconds to clean it up so that we can touch on the other thing that I wanted to address, which is Coulomb's law. So I'm going to get rid of these components. I don't need them. Okay. Bye-bye the angle. Bye-bye this. EC I'll keep. I want that. Okay. And then I don't care about what happens at point A or point B. I don't care. Oops. Okay, so then this goes away. All right, and then theta well, if I need theta, I'll draw it again. But for now, I don't need it. Okay, so now you place Q is equal to, well, Q negative. I'm not going to give it a value at point C. What is the force on Q? Okay. Now, I'm placing this charge here, Q. Now, this is very tricky, and we're going to talk about this multiple times this semester probably, because it's part of the issue of having charge that can be positive or negative. So, Q is a negative quantity, right? I have two options to give you a negative quantity. I can say the letter Q is negative, like this, meaning that you then have to remember when you see Q that it's a negative value, which is in my opinion, a pain in the ass, but some people like that notation, and so I'm not going to take it away from them. And you're going to bump into it anyway. Or I could do this. I could say minus q. Now I like that. I like my minuses out front where I can see them. Okay, it's a negative charge. I don't have to remember shit. I see minus q is minus q. It means the charge is negative. Otherwise, I wouldn't have bothered to put a minus sign in front of it. Okay, so I tend to go with this, but in this particular instance, I went with q negative like that. First of all, so we could have this very conversation. But second of all, to tell you that both are possible and both exist. And yes, I prefer this, but that doesn't mean that that's what you're going to encounter. So let's just stick to q as negative. The problem that you're going to run into is a problem of magnitude and direction, because we're going to write, Fe is equal to QE, right? That's the electric force is Q times E. But the question is, is Q positive or negative, because it has an impact on direction. And so to avoid getting the signs mixed up, because maybe Q is negative, but you forgot, right? You just shove Q in there and you thought you had magnitude, but now it's a negative number, something like that. So to avoid any issue, what I recommend you do is you always find direction just by thinking things through. And then for magnitude, you throw a bunch of absolute values in there if you need to. So what do I mean? I mean this. Let me get rid of this. And let's think about this charge that's negative. It's a negative charge. Is it going to be attracted or repelled to Q0? It's going to be attracted to Q0, right? So the force that is going to be exerted on little q, which is the force of big Q on little q, is going to be a force that is an attractive force. That's why I'm going to draw it in this direction. But now that I've drawn it and I've accounted for direction, I'm only going to write the magnitude of F of big Q on little q, which is why I'm not putting an arrow above it, right? I'm just writing it like this because I want magnitude. Well, what is it? Well, the magnitude is going to be Q times EC, right? But careful, Q is a negative number. It doesn't look like it, but it is. So I'm going to put an absolute value for Q right here. And by the way, what is EC? Well, we know the magnitude of EC, right? It's going to be, based on what we wrote before, it's K Q0 divided by R squared. Okay, so we get K Q0, which is positive, times Q, which is negative, so we have absolute value, divided by R squared. Okay, and it's Coulomb's law, isn't it? Right? Coulomb's law, you could have said, hey, I know what that's going to be. It's, KQ1, Q2 divided by R squared. That's exactly what I get. And that's true. It is Coulomb's law. The problem is you memorize Coulomb's law like this, and when you do, you forget that it's only valid between 2 point charges. You just see Q1, Q2, but you forget that they have to be point charges. So the way that I did it here is very deliberate. I was saying first, let's find E at point C. Right? The magnitude is this. And then let's use the definition of the electric force, which is that it's charge, absolute value of Q, times E sub C, which is the force per unit charge. And then what comes out is this. Okay? But the only reason that this looks like this is because E sub C looks like this. And E sub C is created by a point charge. Now, of course, week 1, we only know about point charges, so why are we having this conversation, right? Well, as soon as week 2 rolls around, we're going to learn that there's other objects that can carry charge that are not point charges and that could create an electric field. And the electric field is not going to look like this, therefore the force is not going to look like this. And so I know I'm harping on this, but the point is, Coulomb's law is only valid between point charges because you need this to be created by a point charge times another point charge. Then you get KQ1, Q2 over R squared. But if this electric field here were not created by a point charge, if it were created by something else, this thing would look different, and therefore this thing would look different. And so the first important thing to remember in this summary is what we wrote earlier, which is if Q0 creates E sub C cannot act on Q0. It's not possible. That's one big misconception. The other big misconception is that Coulomb's law is always valid. It's not true. It's only valid as long as you have point charges. But if you have a point charge and an infinite sheet of charge, Coulomb's law is out the window. If you have an infinite cylinder and a point charge, Coulomb's law is out the window. So Coulomb's law, as straightforward as it is only valid between point charges. Okay, you have to have 2 point charges, Q1 and Q2, for Newton's law, Coulomb's law, excuse me, to be valid. Okay, so that's really important. Right? It's really important to keep that in mind because it's very tempting to, again, if you just think that when you write K, Q1, Q2 divided by R squared, well, all you need is Q1, Q2 to be some amount of charge. Who cares if it's on a cylinder, a sheet, or a point charge? Then you're going to get it wrong. Q1 and Q2 here stand for point charges, right? And again, I want to emphasize this because since we usually start the class by teaching Coulomb's law, because we got to start somewhere, well, then you then start to believe that Coulomb's law works all the time. After all, it's the first thing I was taught, so why wouldn't it be something that I can use later? It's like, well, it does work all the time as long as all the time means problems with point charges, right? So that is fine. But if you don't have point charges, then you can't use Coulomb's law. All right, so that was a little longer than I anticipated the summary to be, but it's also the first live stream for this class, which is, as you already can tell, completely different from Physics 8A. Are there some topics from 8A that transfer over to 8B? Sure. You know, like you have to know forces and components, and yeah, occasionally you're going to get Newton's second law in kinematics, and occasionally there's going to be circular motion, maybe even conservation of energy. So the few things that, you know, transpire from 8A into 8B, but the bulk of it is completely new and completely different. So we have to give some good definitions at first to build a baseline to then continue on and for Gauss's law to make sense and for electric potential to make sense and so forth. Okay, so with that said, let's do a couple problems. This is the first problem I want to do. I'm going to shrink that real quick just to some reasonable size. And I'm going to redraw it anyway because it'll be easier. But this is typically the type of problem that you could encounter. It's probably too easy to be an exam problem, but it's a great problem to review components, magnitudes, and things like that so that we don't get all confused later on. So, and if you're having trouble with this, you really have to sit with it and conquer it because there's many variations and flavors of this problem, and there's no way you make it through the chapter without encountering something like this. So let me just very quickly redraw this. Okay, so here I have Q3. Now Q3 is negative. Then I have Q2. And here I have Q1. And right over here I have point P. Okay, now something else that's super important. We tend to do this, right? This is a point in space. It's a location, and you know, call it point P, call it whatever you want, but we give it a name just to name the location. It is not a point charge. Like, there's nothing there, right? This is just a location in space. Now, can you put a test charge here? Eventually, sure, you can if you want, but the point is not that. The point is point P typically is just a location, is not a point charge. The only point charges that I have are these three guys. Okay, and now what's unfortunate is that Q3 is negative. I just have to remember that. They didn't write it minus Q3, which I would have preferred, but okay, Q3 is negative. I'll just keep it in mind. All right. Now let's get a few things figured out here up here, and we can reuse them later, so I don't overcrowd the figure down here. We have these 3-point charges, and then we're told that a positive test charge Q is going to be placed at location P, so at point P, and it experiences a 0 net electric force. What happens if we put a negative charge at point P, and how's that going to differ if it does? And then can you find Q2 and Q3 if Q1 is positive Q? Okay, so I'm going to need this distance here, R. R is going to be 5D. And eventually, I'm getting ahead of myself a little bit, and you don't have to realize this up front. I'm doing it up front so that I can say, okay, well, this angle theta I'm going to need. I know I'm going to need it. If you don't, you can introduce it later. But I introduce it now because I want to be able to say, well, you know what, cosine of theta, based on this problem, is adjacent over hypotenuse, so it's 4/5 conveniently. And then sine of theta is opposite, which is 3D, over hypotenuse, so it's 3/5. Right? So I already know little r, cosine theta, and sine theta. So when I need them later, I can, just write them out, and you'll know where they come from. So this is just for later convenience. It's prep work that I know I need to do because it's not the first time I'm doing the problem, basically. Okay, now I'm going to draw 2 of these drawings, yeah? Now, why would I draw 2? Well, I want to compare. I want to be able to compare on the left what happens when I put a test charge plus Q here, right, at point P. So this is going to be plus Q versus a test charge minus Q. And I'll get rid of point P because it's kind of getting in the way now. Okay, we don't need it. Okay, so we're told that if I place a positive test charge Q at point P, it experiences no electric force. Now, there's 2 ways that you can experience no net electric force. Either there are no forces, full stop. You've taken Q, and congratulations, you placed it in a vacuum. There's no charge nearby, no net electric force. It's possible. It's not a very interesting problem, but it's possible. Or there's no net electric force because, in fact, there are forces, they just all cancel out. And that's what we have here, right? So if I look at Q1, Q1 is positive. Q1 is going to repel plus Q with an amount of force, I'm just going to call it F1 for now. Okay, so to the left with a magnitude F1. Q2 is also positive, and so Q2 is going to repel Q with an amount of force F2. I don't really care what that amount is yet, but it's going that way. And then Q3 is negative, right? So Q3 is going to attract plus Q, and it's going to exert a force in this direction with a magnitude F3. And I am told that all these forces cancel out. Okay, that in this case, F net as a vector, which is going to be vector F1 plus vector F2 plus vector F3 is 0. Okay, so I know that this is true on the left here. Okay, well, then the question is, for question 1, if I place a negative charge minus Q at point P, what happens? Okay, well, let's find out. Okay, it's minus Q. I mean, it's the same charge in magnitude as plus Q, yeah? Turns out it doesn't even matter, but we'll figure that out in the second question. So you're like, okay, well, minus Q now. Like, well, all right. Well, Q1's negative, right? Or positive, I'm sorry. Q1's positive, and so it's going to attract the negative charge. With what amount of force? Well, it'll be to the right, but it's going to be the same force F1 is here, right? Like, it's the same distance to the same amount of charge and magnitude, so no reason why F1 would be any bigger or any smaller. It's going to be the same F1. Okay, Q2 is positive. Okay, so Q2 is going to attract minus Q, and in so doing, it'll attract it with a force F2, which has the same magnitude as this F2 here, really, because same amount of charge, same distance between the charges, and so on and so forth.
And then, of course, the same is true with Q3. Q3 is negative. It will therefore repel minus Q with a certain amount of force, F3, and this F3 here is the same as this F3 here. Yeah. Now, what's the only difference? The only difference is the direction of these forces, right? This F1 goes to the left, this one to the right. This is up, this is down, this is toward, this is away, right? So really, what you're saying is that, well, if this is true, then if I have minus F1, minus F2, and minus F3, guess what? That's still equal to 0, right? And so here I'm going to get F net is going to be this, right? Because these forces have flipped direction. Okay, this is just to help you think through it, right? It's not the best notation to have pluses here and minuses here, but I'm just trying to say that the only difference between this and this is a minus sign. But if everything is going to have a minus, it's the same thing as minus all of this, and minus 0 is 0. So the point is, let's not get hung up on vector notation. The point is, if you put a charge plus Q here and it experiences no net force, then you can put minus Q here, it will also experience no net force. In fact, you can put minus 17Q, that'll make a difference, right? The reason that it experiences no net force is actually because there's no net electric field at that point. The electric fields from Q1, Q2, and Q3 are going to cancel out. And so here, there is no electric force per charge, so you can put any amount of charge you want, you're still going to get net force of 0, okay? So it's just an interesting thing to keep in mind, right? It won't change anything if you increase the amount of charge, or you make it negative or anything, you will still get no net force. Okay, and so then, assuming that Q1 is plus Q, what are Q2 and Q3? So let's see if we can figure that out. And what we'll say is that, look, we've just made the case that there's no difference between this scenario and this scenario. So pick the one you want, it doesn't really matter. And I'm going to pick this one, just a sec. There you go, sorry, I'm back. Part of the joy of not having the studio finished yet is that I get to listen to very loud trucks driving and interrupting the beauty that is electric force, electric charge, and electric fields. Anyway, so it doesn't matter which one we choose, let's just stick to this one, right? This is good enough. And we're going to say that Q1 is plus Q. Can we figure out the other charges, right? So we know that Q1, Q1 is plus Q. And then we want to figure out Q2 and then Q3. Okay. And we're going to call the test charge plus Q, but like we said, it doesn't matter if it's positive or negative, so it's going to cancel out in the end. Okay, sorry, just muting myself as the trucks go by. Okay, so there's no net force at this acting on little q, okay? I'm going to introduce, like I did before, this angle theta here, because then it's going to give me this angle, and I'm going to need it for the components of F3, right? Now, F1 is easy. It only has an x component. F2 only has a y component, but F3 has both an x and a y component, right? Okay, so let's first agree that in magnitude, F1 is equal to, now it's between 2-point charges, right? So they're both positive, so it's going to be K Q1 Q divided by, now this distance we're told is 4D, this is 3D, and of course this is 5D, right? Divided by the distance between Q1 and Q is 4D, and if I square that I get 16D squared. Okay, what's the magnitude of F2? Well, F2 is between two positive charges, all right? So it's going to be K Q2 times Q divided by the distance between the two squared, which is 3D, and if I square 3D, I get 9D squared. And then just the magnitude of F3, which, we're still going to have to get F3x and F3y from F3, but in magnitude, F3 is equal to, well, it's between positive charge and negative charge. So careful, I need an absolute value around Q3. It's going to be K, absolute value of Q3, so that this is a positive number, times Q, divided by the distance between these two charges is 5D. If I square 5D, I get 25D squared.
Okay, that's F1, F2, F3 in magnitude. Now that doesn't quite get me what I need, but it gets me set up properly to do the following, right? There is no net force along X, and there is no net force along Y. And that comes from saying that, well, there really is no net force acting on the point charge plus little q. So there can be no net force in the X direction and no net force in the Y direction. Okay, if that's true, and this is our equilibrium condition, then F net X is equal to what? Well, based on the forces, it's equal to minus F1, because it points to the left. F2 doesn't have an X component, and then plus F3X, and that's going to be 0. Okay, and then F net Y is going to be, F1 does not have a Y component, F2 upward minus F3Y downward is going to be 0. Okay, so then let's figure out what F3X and F3Y are, because it's going to be helpful, right? So let me perhaps, do I have room to do it? I'll do it right here, and then I'll rearrange stuff once I don't need to see this figure anymore. All right, so I'm going to have F1 is equal to F3X. F3X is the adjacent component, so it's F3 cosine theta. Remember, we said cosine theta is 4/5, right? So then I have F2 is equal to F3Y. F3Y is the opposite component relative to theta, and so it's F3 sine theta. So let me make a copy of this. I'll bring this down here. We'll just gray it out because it's not really part of solving, it's just for us. And then let's bring this down here, okay? And now we can solve and be on our way, okay? Remember that, by the way, that Q1 is little q, right? And just if we're trying to remember things, cosine theta is 4/5, and sine theta is 3/5. Okay, this is all the stuff we derived earlier. I'm just bringing it here because I don't want to scroll up and down. Okay, so F1 is K Q1 little q divided by 16d squared, and that's equal to F3 cosine theta. So it's K absolute value of Q3 times Q divided by 25d squared, and cosine theta is 4/5. I'll just leave it like that for now. Okay, then we have F2 is F3 sine theta. Well, okay, F2 is K Q2 times Q divided by 9d squared is equal to F3, K, absolute value of Q3, Q divided by 25d squared multiplied by 3/5. Okay, now this is going to clean up, right? Now I'm going to clean it up. Bear with me, I'm just going to do this. I'm going to get rid of Q on either side. Now if you look at what's left, let's just think about what's left. What you really have here is E1 is equal to E3 cosine theta, which makes sense. Really what you're saying is that there's no force along X because there's really no net electric field along X. And same thing here, this is E2 is equal to E3 sine of theta. So yes, we wrote it in terms of force at first with Coulomb's law, which is fine, but really
what it boils down to is that there's no net electric field. So it makes sense that that's what our system simplifies to at first. Okay. Now, of course, the simplification rather goes further than just Q. I can kill K, and I can kill D squared. All right, so this is going to trim things down quite a bit now. Okay, so I have Q1 divided by 16 is equal to 4 times absolute value of Q3 divided by 125. And then this is Q2 divided by 9 is equal to 3 absolute value of Q3 divided by 125. Okay, and by the way, I know that Q1 is equal to capital Q, so let me start with that. Okay, so I can solve. Let me solve for Q3. I'll solve for absolute value of Q3, and then we'll have a conversation here. Okay, so absolute value of Q3 is going to be 125Q divided by 4 times 16 is 64. Now what that means is that Q3, because it's a negative charge, really is equal to minus 125Q divided by 64. Okay. Again, this is why I really don't like this whole Q3 is implicitly negative. You have to remember when you see Q3 that it's a negative number, because otherwise you wouldn't choose the right sign here. So fine, it is what it is. I would have put my minuses out front from the get-go, but point is Q3 is a negative amount of charge. It's negative 125Q over 64. Cool. If that's true, then if I know absolute value of Q3, then I know Q2. Q2 is a positive charge. It's going to be 3 times 9 is 27. Absolute value of Q3 divided by 125. Okay, well that's 27 divided by 125 multiplied by 125 capital Q divided by 64, and that's going to be equal to 125 goes away, 27Q over 64. Okay, so I mean, again, a manageable problem, but a good problem to go from from lecture to discussion, right? It involves things that we learned in lecture, Coulomb's law, the electric force, direction, magnitude, all that, and then we can apply it to this type of problem. But here's the truth of the matter. It's like somebody has to teach you how to think through these problems, set them up, and solve them. And I do it because, first of all, because I like to. Second of all, because it's, it's pretty much what I do for a living. I mean, I tutor students all the time, and so I enjoy doing it, and I think I can, give you some good advice to get started and get unstuck at first. And second of all, because it turns out that it didn't used to be as much, but more and more over the years I've heard that, when you go to discussion, look, are there some good GSIs out there? Yes. Are there some bad ones? Yes. And I don't know what the proportion is, and I'm not here to, give notes. But this idea that you go to discussion, you sit as a group, and you think through a problem that, that's a hard physics problem, or even if it's this one, because you could argue this one isn't that hard. How are you supposed to know how to do this and think through this and set it up properly, right? If you've never been shown before. Like, I don't have a problem if, let's say that we were in discussion and I did this on the board and I walked you through it. And then I said, hey, you know what? I have a variation of this problem. It's a little harder. I want you to think about it as a group. That's fine. I'm okay with that, because you at least can lean on the stuff we just did, and maybe you figure out how the new problem is different and a little bit harder, and then we have an interesting conversation. But if I throw this at you just when you walk through the door and say, hey, look at that, and meanwhile I'm going to be on my phone or whatever, and not really teaching you, that I have a problem with that. So, in fact, it infuriates me beyond belief. So
it came about. I heard about it more and more over the years, and I decided to live stream because um, it just seems wrong that you would end up in a group like that with a GSI that maybe doesn't care at all or as much, and maybe the GSI is just doing what he's told to do. That's also very possible. So, we were told to teach a certain way and to do certain things. My opinion is that it was the wrong way, so I didn't do it, and I do what I want. But a lot of GSIs just follow along and say, "Oh, it's what I was told in the weekly meeting, so this is what I'm going to do." And who decides what you're going to do is a bunch of professors that sit on committees and, in my opinion, don't know how to teach. But anyway, not here to, get into that conversation. The big idea is that I live stream and I teach you these things because I enjoy it, but also because I think for some of you it makes a difference, and I always enjoy hearing from those of you for whom it has made a difference, so thank you. All right, so this is the next problem I want to do. Now, before I do it, let's go back here. Let's zoom out real quick. What do? We talked about electric fields. We talked about point charges, and we said, well, there's a formula for the electric field created by a point charge, and then there's a formula for the electric force. Tried to kind of start to bring everything together with this example to explain our hat and all that, and then to talk about Coulomb's law, okay, which is a special case. And then we're like, okay, let's do a problem here with multiple point charges. Okay, so everything we've done so far has been about point charges. And point charges are, in fact, the focal point of this first chapter in Physics 8b. And for a long time, most, if not all, professors only focus on point charges when teaching this chapter, because it's technically, according to the registrar, a calculus-free physics class. It is an algebra-based physics class. This is not 7b, it's Physics 8b. And so we're not supposed to do calculus. And nothing that we've done so far has involved calculus. Okay, well, be that as it may, as, the years go by, we have curriculum inflation, and professors do what they want for the most part. And they decided that there was a great collection of problems that we should do that fall under this chapter if you're taking Physics 7b, which is called the slice and dice method. In other words, what we're saying is that not everything in the world is a point charge. Sometimes you get shapes like a semicircle, or maybe a ring, or maybe a disk even, right? It's not a ring, it's an entire disk that has charge. What is the electric field that something like that creates? And you're like, well, hell if I know. I don't. I had no clue. And it's a good answer because it's not a point charge and all you know are point charges. But this is called the slice and dice method. It's to deal with objects that are not point charges and have a certain shape and size. Namely, those objects are the semicircle, the ring, the disk, the solid disk, the annulus, which is a disk with a hole in the center, so like a washer. It's very similar to the disk anyway. And then the finite rod of charge. Those are the slice and dice ones that you can do by hand. And whether you have Bordell or Speleo, it doesn't matter. There is no way on earth you go through the class without having to do slice and dice. Okay. I would actually say it is far more likely that you will encounter slice and dice with Bordell even than with Speleo, because she really likes calculus, and her argument is that Physics 8b should be done with calculus, and we can have a debate as to whether that's right or wrong, but it doesn't matter because she's teaching and she's going to give you shit like this. So we need to talk about the slice and dice method. And we want to find the electric field at the center of this semicircle of charge. So, now this is just one of them, and all the other ones I listed you should be familiar with too. So the bad news is that it involves calculus. The good news is there's only one way to solve these, right? So once you know how to solve the semicircle, the ring, the disk, the annulus, and the finite rod, you can just literally basically memorize the solution and copy paste it. It'll work every time. It's always the same thing. Right? I don't advocate blindly memorizing solutions to problems in physics, but it will work for slice and dice. So you know what? That's always an option if you can't make it make sense and you can't recreate the derivation on your own. Okay, so bear with me here. I'm going to draw two of these, and there's a reason.
It's two of the same, but I want to draw different things on each one. Okay. All right, so first things first. This has an amount of charge Q distributed on it. Okay, so what we're going to do is we're going to introduce what's called lambda. Okay, lambda is going to be Q divided by the length of the semicircle, which is half the circumference, and since the circumference is 2 pi r, lambda is just pi r, Q over pi r, so half the circumference is pi r. This is called a linear charge density. Okay, now what is a charge density? It is a charge per something, typically a charge per meter, a charge per meter square, or a charge per meter cube. So a charge density is a charge distributed throughout an object. And if the object is a line, like the semicircle, I just divide charge by length. If the object is a surface, like a sheet, I divide charge by surface area. And if an object is like a sphere, so it has a volume, I divide the charge by the volume. And those are going to be my charge densities. And lambda is charge per length, and then sigma is charge per area, rho is charge per volume. But the point is here I have to introduce lambda because this charge is uniformly distributed over the length of the semicircle. Now, here's the main problem that I have. The main problem that I have is that I only know the electric field created by a point charge. So I have no other formula, excuse me. So because of that, I cannot tell you what the electric field created by this thing is off the bat. What I can do is the following. I can take a slice here so small that I can treat it like a point charge. Now that slice, let me redraw it here, and I'm drawing it quite big, but you're going to have to remember a little bit of calculus here. This is going to be arc length. In fact, it's what's called the infinitesimal arc length. It is the shortest arc length that I can imagine that's not 0, right? So you can make this as short as you want in your mind. It just cannot be 0, which of course is quite a mental trip in the first place, because what does that even mean, right? Because however small you make it, you could probably still make it smaller. You just can't make it 0. Okay, but without getting hung up over the philosophical meaning of ds and d theta being the smallest angle you can imagine that's not 0, we have to remember that if the radius of this semicircle is r, then ds is r d theta. Okay, so that's really important. And here I'm going to take this little piece ds, and what I'm going to say is that this piece is so small, it's the smallest length that I can imagine that's not 0. And so it is no different than a point charge. By the way, how much charge does it have? Well, lambda is charge per length. So if I multiply lambda by this tiny length, I actually get the tiny amount of charge that it has. I'll call it dq. So I have something here that is so small that it might as well be a point charge. And so if it's positive, it's going to create an electric field right here, which is going to have a magnitude, we're going to call it dE, right? And then I know what the magnitude is because this is a distance r, and I'm saying dq is so small that it might as well be a point charge, right? So it's k dq divided by the distance. Now it should be little r squared, but little r is the distance from here to here. It's really the radius, big R, of the semicircle. Now dq is lambda ds, so this is k times lambda. By the way, ds is r d theta divided by r squared. Okay, the r kills the square, and I get k lambda d theta over r. Okay, so that's going to be the tiny piece of electric field created at the center of the semicircle by this little piece of semicircle that is so small that I can treat it like a point charge. All right. However, I only took a piece of my semicircle. this is not accounting for the entire semicircle, right? So if it's just a little point charge, a little piece of it, how many do I have? Well, infinitely many, really, right? I could say, well, I'm going to add them all up. I'm going to do a sum. But the truth is that I'm going to do a continuous sum, so I'm going to really integrate this over the semicircle, okay? And by the way, to do that, I need some parameter or variable of integration. Looks like it's going to be theta, right? When you integrate f of x dx, the dx tells you you are integrating with respect to x, right? And so if I have d theta, I'm going to integrate with respect to theta. I'm going to make this theta so that this angle here is theta. It actually doesn't matter. You could make this angle theta all the same if you want, as long as you adjust the bounds. But if theta is the way I defined it, then this vertical corresponds to theta equals 0. Down here it's going to be theta is minus pi over 2. And then over here it's going to be theta is equal to pi over 2. Okay, I was going to use that later. So I have to integrate this to get the electric field at the center. Well, sort of. Okay, here's the biggest error, the biggest, not misconception, just the biggest thing that students forget when they do the slice and dice. If you make it this far, you're usually so happy with yourself that you're like, okay, shit, all I got to do is integrate, and integrating d theta is super easy, and it's just going to give me from minus pi over 2 to pi over 2, it's going to give me pi. We're done, let's go. Okay, the problem is if you're doing that, you're only remembering magnitude, you're not remembering direction. So what do I mean? We have to argue that the electric field at the center of this semicircle is going to have a component horizontally and a component vertically, right? And in fact, we're going to do better than that. We're going to argue that the horizontal component is 0 by symmetry. And the reason why is that for every slice dq to the left of the vertical, I can take the same slice dq on the other side, and that slice dq is going to create the same de like this. And by symmetry, if you look at those two, you can convince yourself that the horizontal component here of the one on the left and the horizontal component here of the one on the right, they're going to nick themselves. And this happens for every dq you can imagine on either side, right? So horizontally, by symmetry, but you do have to argue this, by symmetry, Ex is equal to 0. Meaning that I don't care about the x component of dE, which would be dEx, because if I integrate over the semicircle, which will account for the symmetry, my integral is just going to output 0. Right? So why go through the pain of computing an integral just to get 0? Like that's math 1B PTSD. Like you compute this great big integral and you get 0. You're like, oh no. So we're not going to compute the x component. We don't care. We only care about the y component. Okay. Now what is the y component? Well, it's this guy. And dE sub y is equal to dE cosine theta. Right? It is the component adjacent dE relative to theta. Okay, well, if that's true, then I'm going to say that let's call it EPY. EPY is going to be the integral of DEY. Wow, that's terrible notation. Okay, so apologies. Hold on. I gotta be able to live with myself here. Here we go. The EY is the integral of DEY, and just to be sure, DEY is DE cosine theta, so it's K lambda d theta divided by R. That's just DE, and then cosine of theta. Okay, and if you look at this, this is constant, this is constant, this is constant. Our variable of integration is theta. Okay, so then I just need to write the bounds on this integral in terms of theta. It's going to be the integral from theta is minus pi over 2 to theta equals pi over 2 of this thing. All right. And so this is going to be, well, integrals don't care about constants, so k lambda over r can go live out here. And then we're going to get the antiderivative of cosine is sine. Usually antiderivatives are given, but you may want to just quickly brush up on them just for peace of mind there. Okay, between minus pi over 2 and pi over 2, let's evaluate this little thing. That's going to be k lambda over r. And that's going to be now sine pi over 2, which turns out is just 1, minus sine of minus pi over 2, which is minus 1. So this actually doesn't cancel. I just get 2. This is 1 minus 1. So here I'm going to get 2 k lambda over r. Okay, the only thing that's left to do is to recall that lambda is not something I was given. If it were, then I'd be done. Here I computed it. It's q over pi r. So this is going to be 2k q over pi r squared. And the direction is going to be downward. All right. So this is what's called the slice and dice method, because you're going to slice your charge distribution up into a little piece that's so small that you can treat it like a point charge. And that's good because then you know what dE is, right? You can use k dq over r squared to find the magnitude of dE. You then typically have to argue symmetry, and then you integrate the component that you want over your charge distribution, right? It's a bit of an art. It's a very non-intuitive way of doing physics, but it is the way you would do all of physics if you were taking 7b or 7a. It's just that here that's not how it kind of is off topic and outside the scope of the course in theory, except in practice everybody does it. So if it doesn't make any sense to you that you would proceed this way and that it would give you the answer, your resort is to just go do all the slice and dice problems you can find. There's only a handful. You can just memorize all of this. It'll always work. There's only one way to solve it, and there's only one answer. So I don't typically advocate memorizing solutions to physics problems. That's usually how you shoot yourself in the foot. But for the specific case of slice and dice, because it's just the semicircle, the ring, the disc, and the rod, yeah, I probably would just memorize them, at least at first, right? And then if you do them a few times, maybe it starts to make sense and you can just do the derivation without memorization. But I really wanted to talk about that because it's something that's very common. You'll see it in a lot of old exams. And often it's not even the hardest part of the problem. It's like, okay, well, we're going to throw the semicircle in here because at least the first question, it's 3 points for everyone. They'll just find the electric field at the center. And then we build on that, and then the problem has 2-3 more questions that, those are the hard questions, right? At least in the eyes of the person who wrote it. So it's important to know that slice and dice is a thing, even though, of course, the bulk of this chapter is the point charge and the electric field that it creates and the electric force that it experiences. But, you should know about slice and dice in the first place. So with all of that said, that is all I wanted to talk about this week. Next week, we'll be back with Gauss's law. As always, if you have questions, feel free to reach out. I'll try to do some interesting questions I've been asked at the beginning of each live stream. I'll try not to forget, but sometimes I get some really good questions that are worth just going over because they're either very common, I get them from many different students, or they're just solid questions that clarify concepts a bit. So I like to incorporate that. And I will see you next week for this. And in the meantime, just make sure you stay on top of 8B. It's a very dense class. It goes very fast. Midterm 1 is going to be there real soon, and there's a lot of skills to conquer before midterm 1. So not to scare anyone, but this is not the semester to wait till the end of September to start studying for midterm 1. That's gonna be very, very painful. And for those of you who need help, either tutoring or the master class, just heads up, that I have limited spots. I'm not trying to pressure sell anyone or to force you to do something you don't want to do. I'm just saying I have limited spots because there's only so many hours in the day, and when they're full, they're full. So I'm always happy to help you if I can, but if you wait too long, usually it fills up, and then I can't add hours to the day. So anyway, with all of that said, as always, thanks for watching. I appreciate it. Thanks for the feedback. I appreciate that too. Have a great week, and I will see you next week for more of these adventures. Take care.